Okay, welcome to the last part of Math 0007, which is our section on group theory. So we're going to begin by talking about binary operations. So here's the definition, the formal definition of a binary operation. A binary operation on a set X is a function from x cross x to x. For example, you can think of plus as a binary operation on the set of integers. It takes a pair of integers a, b as input, and it outputs another integer a plus b. So we tend to use a special infix notation for binary operations, just like we do for addition or multiplication. And what infix means is that instead of writing plus 2, 3, we write 2 plus 3. Or instead of writing times 2, 3, we'd write 2 times 3. Okay, let's see some examples of binary operations. So number one, plus is a binary operation. So binary op for short on a set of natural numbers, n. If you add two natural numbers, you get another natural number, so plus is a binary operation on n, and equally on the set of integers, z, or on the set of real numbers, r, or the set of m by n real matrices, and so on. So, also, if we take subtraction minus, that is a binary operation on the set of integers. If you subtract two integers, you get another integer, so this is a binary operation. On the other hand, subtraction is not a binary op on the set of natural numbers. And the reason for that is if you look at the definition of a binary operation, so a binary operation on the natural numbers has to take two natural numbers, a pair of natural numbers as input, and give you another natural number as output. But if you subtract two natural numbers, you don't necessarily get another natural number. For example, if I take 1 minus 2, well, whatever that is, it is not a natural number. Okay, a more interesting example then of a binary operation is here composition of functions. So this little circle is supposed to be composition of functions. So this is a binary operation on the set Sn. So you'll remember we defined Sn in the very first part of our course to be the set of all bijections from the set 1 up to n to the set 1 up to n. In other words, all the permutations of the set 1 up to n. The reason that is a binary operation, composition of functions is a binary operation on Sn, is that we have a result telling us that the composition of two bijections is again a bijection. The property that when you do a binary operation to two elements of a set X, you have to get another element of the same set X is sometimes called closure of the binary operation. But it really is part of the definition of the binary operation. You can see there we defined it, a binary operation, to be a function from the set x cross x to x again. So closure isn't a special property that a binary operation might or might not have. There's no such thing as a closed binary operation. Every binary operation has to take two elements of a set X as the input and give another element of the same set X as output. Otherwise, it's not a binary operation. Okay, now we're ready to define a group. So here is the formal definition of a group. We take a set G and a binary operation star on G, and we say that the pair G star is a group if it satisfies these three properties. So these three properties are called the group axioms. Let's label this. So these three things here are the group axioms. Okay, so axiom number one is called the identity axiom. That says that the set G has to contain an element E which has the following property. So for every element little g and big G, it has to be the case that E star G and G star E are both equal to G again. Okay, next axiom is the axiom of inverses. This says that for every element little g in big G, there has to exist another element h in big G with the property that G star h and h star G are both equal to this element E, which comes from the identity axiom. So finally, the associativity axiom, the final one, says that for all elements G and H and K in our set capital G, it has to be the case that G star H star K, bracketed like on the left there, has to be equal to G star H star K. Okay, so these three conditions then are the group axioms, and if you've got a group, so a set and a binary operation obeying those three rules, then star, the binary operation, is called the group operation. Okay, one small bit more vocabulary. The element E, which is provided by the first axiom, the axiom of identity, is called the identity element. Or sometimes just the identity of the group G. So another piece of vocabulary you will hear is that people will say something like G forms a group under the binary operation star to mean that G star is a group. Okay, some more notation then. Just like when we multiply two numbers x and y, we'll often write xy instead of x times y. We do the same thing in groups and binary operations. So when there's no danger of confusion, we often write just xy instead of x star y, and that's where star is an operation on some set G, and x and y are elements of that set. Okay, so those are our three group axioms. And what's really remarkable about the theory of groups is just how many things you can prove about groups solely using the definition, so solely using those three axioms. So what we're going to do on our next slide is to actually try and prove something which is valid in every group, which means we have to do it just by using those three group axioms. So here we go. Here is the lemma we're going to prove. It says that if you've got a group G star, and the identity element in that group is lowercase e, and lowercase g is an element of this group, then there is a unique element h in G with the property that G star h and h star g are both equal to the identity element e. Okay, well, we know that at least one such h exists because that's what the inverses axiom said. So what we have to show is that there is only one such element. So in other words, what we need to show is if H star G and G star H is equal to E, and if we've got another element satisfying this, so let's call that H prime star G, G star H prime, those are both equal to E as well, then what we need to prove is that actually H equals H prime. Okay, so what we're going to do is write down a proof in which we carefully spell out which of the group axioms we use at each step of our proof. So let's try this. Step 1, well, what do we know? We know that H star G must be equal to H prime star G. That's simply by assumption. Right, both of those things are equal to the identity E, so they're certainly equal to one another. Okay, what we're now going to do is we're going to take this equation and we're going to multiply on the right by H. So when I say multiply, what I really mean is we're going to apply the binary operation star to both sides of this equation and H. So let's do this. H star G star H equals H prime star G star H. And here this is just obtained from the previous line by right multiplying by H. And when I say multiply, what I really mean is to apply the binary operation star together with H as the second input to that binary operation. So it's quite common when we're talking about groups to write them using this multiplicative notation which we discussed on the last slide, and to talk about multiplication rather than applying a binary operation or doing the group operation. Okay, what can we say next? We have an axiom which says that the binary operation star is associative, and associativity lets us re-bracket these expressions how we like. So we're now going to use associativity, and what we get out of associativity is that this is equal to H star G star H, and on the right it's equal to H prime star G star H. So this is by associativity. Okay, our assumptions tell us about these two things, G star H. It tells us those things are equal to the identity E. So let's write this down. And here we have H star E, and here we have H prime star E. Again, this is by assumption. Okay, but lastly, what was the defining property of the identity was that when you starred it with something, it didn't change that something. So the identity axiom would tell us that H star E is just equal to H again. And equally, that H prime star E is just equal to H prime again. So this is by the definition of the identity. So this lowercase e was the thing which satisfied the identity axiom, and the identity axiom tells us that H star E and H prime star E are equal to H and H prime. Okay, and that completes our proof. We've done this proof of the lemma. All right, so now we've proved something about groups, but we don't have any examples of groups at all. So what we're going to do in our next short video is we're going to explore some examples of groups.